Welcome everyone. Today we are going to be learning a very important topic of graph, that is topological sorting using Kahn's algorithm. So let's get into it. So first of all, what is topological sorting? Topological sorting is for directed acyclic graph, or so we say DAG, is a linear ordering of vertices such that for every directed edge u, v, vertex u should always come before v in the ordering, and it is not at all for if the graph is not a DAG or directed acyclic graph. So let's learn it with example. Suppose this is our given graph and this is the topological ordering that is already been given. So what we want to do is first we're going to check if that ordering is right or not. So what was our definition? That every ordered pair u comma v, u should always comes before v in the graph. So let's check. Here the first vertex is 5, so 5 should come before 2 and 0. So is it coming before 2 and 0? Yeah, it is coming before 2 and 0. Next is 4, so 4 should come before 0 and 1. Is it coming before 0 and 1? Yes, it is coming before 0 and 1. Next it's 2, so 2 should come before 3. Is it coming before 3? Yeah, it is coming before 3. Next it's 1, so as you can see 1 has no outward edge, so it can pen last, second last, it doesn't matter as long as it's come after the 4 and 3. So okay, similarly for 0. So one thing that you have noticed is the order of 0 and 1 doesn't matter if 0 comes last or 1 comes first. So what I'm trying to say is there are more than one possible topological sorting of the following graph. For example, this is another topological sorted order. So if you want to try, you can also check every vertex is like before its corresponding edge. So the thing to notice in this is the first vertex in the topological sorted order is always the vertex which has and 0 as in degree. For example, in this graph, the 5 and 4, they have no vertex as incoming edge. So instead of directly jumping to the algorithm, what we're going to do is we're going to try to understand how we get into the algorithm. So as we can see from the fact that the first vertex will always be with the in degree of 0. So let's just try and manipulating that algorithm. Okay, so let's just say we have two choices to take first vertex, either 5 or 4. So let's just say we choose 5. Okay, so after choosing 5, let's say we remove that 5 from this graph. So we'll put 5 here and remove that 5 from here. So now, which is the second vertex that have 0 in degree after removing? So as we'll remove the 5, this 2, 0 and 4, they'll become, this 2 and 4 will become the 0th in degree. So we can either choose 2 or choose 4. Let's just say we choose 4. Then we remove our 4. Then this 5 and 4, they both are removed and they have put it into this order. Then we have 2, 0 and 1. These three we have that have 0 in degree. So what we're gonna choose? Let's say we're gonna choose 2. Then 2 we're gonna put here. We're gonna remove 2. Then we have 3 vertices that have 0 in degree. 3, 0 and 1. We'll choose 3. Oh sorry, this 1 doesn't have 0 in degree as this 3 is pointing towards 1. So we have 0 and 3. So we can take either 3 or 0. So we'll take 3 here. So then we will remove 3. Then we have 0 and 1. You can choose in both order. You'll get this, or you can swap 0 and 1. It doesn't matter as long as the next vertex comes before its corresponding edge. Okay. So we're gonna formulate this algorithm into steps. But first, as in the previous slide, that I've said that this topological sorting is not valid if the graph is not a DAG. So we can prove it. There's a simple proof for the above fact that if that a graph is DAG that does not contain cycle, which eventually will mean that all the paths are of finite length. Now let S be the longest path from source to destination. Since the S is the longest path, there can be no incoming edge to U and no outgoing edge from V. If this situation has occurred, then S would not be the longest path. So in degree of u equal to 0 and out degree of v equal to 0. So that's just it. It's just simple proof. You can search it on net. So let's move on to the steps. First of all, the basic concept that we are working in this algorithm is a directed acyclic graph G has at least one vertex with in degree of 0 and one vertex with out degree of 0. So let's jump on to steps. Step 1. Compute in degree, that means the number of incoming edge, for each of the vertex present in the DAG, and initially is the count of the visited node as 0 because initially we didn't visit any node. Then step 2. Pick all the vertices with the in degree as 0 and add them to a queue. So we're going to be initializing one queue and we have to put all the vertices that we have calculated the in degree that are 0 in that queue. Okay. So step 3. Now we'll remove a vertex from the queue. That is the dequeue operation in any language that you perform, and then increment the count of visited node by 1 since we visited that node, and decrease the in degree by 1 of all of its neighboring nodes. So what does it mean? As I've explained in this initially, if we're going to take 5 that has the in degree of 0, when we remove, the in degree of 2 will be reduced by 1 and 4 will be reduced by 1, whatever the in degree was before removing 5. Okay. So then if in degree of neighboring nodes, as soon as we decrease the in degree by 1, if the in degree of the neighboring node is reduced to 0, then we're going to add it to the queue and we're going to do a while loop, that is repeat the step 3 while the queue is empty. And this is just another condition. If the count of the visited node is not equal to the number of nodes in the graph, then the topological sort is not possible for the given graph, or the graph is directed acyclic, is not a DAG. So let's jump to the coding part. So this is the Geek for Geeks question for topological sort. So given a directed graph, let's read the problem statement. Given a directed graph, you need to compute the function toposort, which returns an array having the topological sorted elements of the array and takes two arguments. The first argument is the graph, that is a graph represented by the adjacency list, and the second is the vertices n. So it is already written that there can be multiple topological sort of the graph, and the driver program will automatically check if your topological sorted order is in one of them. Okay, so these are the input and output. So like we'll return the array with the topological sort of this graph, then it will output as 1 if our topological sort is correct and 0 if it's not. So let's jump directly into the code. So I have already coded it and it's with the comments. If you want to have this code, I'll leave the link in description, but first we're gonna read and explain it how it works. So this function is a static type int topological sort, which is accepting two arguments, that is array list of array list, then an integer n, in which n denotes the number of vertices as it's written here. Then first what we're going to do is we're going to initialize one result array in which we're going to be storing that particular topological sorted order of length n. Okay, then we're going to initialize one queue to insert our nodes with in degree of 0. We're going to name it q. Then we have to make an array of in degree with the length of n. So then we're going to initialize that in degree with 0, as initially we're considering that all the in degrees are 0. Then we're going to populate that in degree array. So we have to traverse the array list of array list and for each one of that particular vertices, if it's connecting to some vertices, we're gonna increase the count by 1. So after this we'll have our in degree array with each and every vertices with in degree field. This is for the checking of the in degree array. Then what we're gonna do is we are checking initially after populating this in degree array what are the vertices that have in degree of 0. We're going to add that to Q. Now our while loop starts. If our queue is not empty, what we're going to do is I'm taking the top of the queue into the current node, and if my a is less than n, I'm initializing this a to 0 just in case. Well, if you're going to remove this, it doesn't matter, but it's just in case because a should be less than our length of our vertices. I'm going to storing that particular vertex with the in degree of 1 to the resultant array, and I'm going to increment the a. Okay, then we're going to remove this node from the graph and decrease the in degree of the corresponding nodes. So we're going to again traverse the array list, and what we are going to do is if that particular has like vertex has some corresponding edge, we're going to reduce their in degree to 1. It means we are decrementing their in degree minus minus, or we can do minus 1, whatever is suits for you. So if at the same time, if the particular in degree of that edge, oh, sorry, my bad, vertex is 0, we're going to add that vertex to the queue. So this while loop will continue and it will come out as soon as we have visited all the nodes, and we're going to be returning the result. So let's see if that code works or not. So the time complexity of this algorithm will be O of V plus E, because we have to visit all the vertex and explicitly see our output is 1 and 1, that is it is accepting. Let us submit the solution. Okay, so back to on time complexities. So we have the time complexity of V plus E as we are visiting every vertex, and explicitly we are also traversing every edge. As you can see, it's the correct answer. So I'll leave the code in the description if you want, and if you have any clarification, please comment. Thank you for viewing this video.